Welcome back, everybody. We start 5.1 and 5.2 polynomial functions. So today will be about the characteristics of a polynomial function. So we have covered polynomials before, what it means to be a polynomial, but now we're going to sketch the graph of a polynomial given certain components. So a lot goes into it, but it's simple. Let's try not to overcomplicate it, right? Okay. Shouldn't say math is simple. It's not simple, right? Okay. So to start with, we have the definition of a polynomial function. A polynomial function of degree n is a function of the form f of x equals a sub n times x to the nth. And that first term is called the leading term, right? So this first term is called the leading term. And the leading term actually tells us a lot about a polynomial. It tells us how the graph is going to be sketched, right? It gives us that much information. And then everything else is the values of x or powers of x in descending order. So let's say the leading term was x cubed. Then the next term, let's say this was x cubed, then it'd be x squared, and then you'd have plus x plus 1. So you go from highest power to lowest power in descending order, and you end with the constant. Remember, a constant is just a number without a variable. So that is just a polynomial function. And remember, to be a polynomial function, your exponents, your degrees, your powers must be whole positive numbers. Or like it says here, oops, not there. Like it says here, your powers must be non-negative integers, and your coefficients must be real numbers. Okay. I'll say leading term, and then down here I'll just say that's the constant. Okay. Next exercise is just determining what is a polynomial function. Okay. So the first one, 5x cubed minus 1/4 square x squared minus 9. This is a polynomial function because the exponents are whole positive numbers. So this is a polynomial, and it says if it's a polynomial, state the degree and identify the leading term. So zoom in. This is a polynomial. Degree is 3. The largest degree is 3. And the leading term is 5x cubed. Okay. Next. The square root of x. Is this a polynomial function? Well, the only way to find out is to convert from radical to rational exponent. So you would get x to the 1/2, since this is a square root. 1/2 is positive, but 1/2 is not a whole number. So this is not a polynomial. This is a radical function, an even radical function. H, is this a polynomial? Well, you do have degrees that are positive whole numbers, but does this function h of x look exactly like this function f of x up top? And when I say does it look like it, do you see a fraction anywhere? And the answer is no. So h of x, we have seen this type of function before. It is not a polynomial. It is a polynomial over a polynomial, but when you have a polynomial over a polynomial, that is considered to be rational. And then the last two are tricky. Polynomials or not? And the answer is yes. These are polynomials. And the reason these are tricky is because these are called the zero polynomials. Because if we attached a variable to it, the power of x would be 0. These both are polynomial functions. If I were to graph these functions, f of x equals 9 would be a horizontal line. And the domain of this line is negative infinity to infinity, which also is the domain of a polynomial. And if I were to graph f of x equals 0, well, that's a horizontal line as well, whose domain is negative infinity to infinity, which is also part of being a polynomial. So, just a little tricky. These are called the zero polynomials. And just for quick reference, if you're wondering like, well, I thought x is 0 with the x of the 0th was 0, that is incorrect. Because remember, anything raised to the 0th power is always 1. So that means that would become 9 times 1, which just gets us back to 9. So remember, anything raised to the 0th is always 1. It is not 0. Oops. Nope. Nope, stop it. There we go. Okay, so we've identified those type of functions before when we found domain in 3.1. Like I said, today is about getting the characteristics of a polynomial and sketching its graph based on those characteristics. And the first thing we have up is something called the leading term test. Like I said before, the leading term gives us almost all the information we need. The leading term can tell us if our function opens up, opens down, opens left, opens right. That's what the leading term tells us. And it is all based on the sign of the coefficient and the exponent of the leading term. Exponent, power, degree, all mean the same thing. So that's what the leading term tells us. So, given a polynomial in standard form, so again, when I say standard form, we saw this above. Standard form means highest power to lowest power, ending on constant. This is just a more complicated way to write a polynomial. But it does show standard form. Okay, the leading term is, remember, the leading term is a sub n times x to the n. When I say sub, I say subscript, right? A subscript n times x to the n. Okay. So the leading term is given by a sub n times x to the n. And that leading term can tell us everything we need as the values of x approach infinity or negative infinity. So this means we're going to come across 4 cases, okay? 4 cases. All right, so the first 2 cases happen if the degree of my polynomial, of my leading term, is even, and if my leading coefficient is positive, or my leading coefficient is negative. So let's look at the first case. So I'll zoom in here, I'll say this happens if our degree is even, right? Or, yeah, n is even, so an even degree, right? And the first case is if the leading coefficient is positive. Being greater than 0 means you are positive. So with that being said, let's think, I need this right there, there we go. Let's think of some even degree polynomials. What is an even degree function? What is the smallest even power? And the smallest even number, even power, is going to be x squared. And then we could say x to the 4th, x to the 6th, anything even, x to the 100th. So these are all even degrees. And right now, my coefficient on all of these is 1. But again, it doesn't matter what the coefficient is. Whoops. All right. I can have 2, 3, 7, and 25 here, right? We don't care what number the coefficient is. All we care is that if the coefficient is a positive number. So what this means is that for case 1, if we have an even degree and our leading coefficient is positive, just like these examples over here, this means that our end behavior, and we're only looking at the tails of how it's going to open, this means that if I have an even degree, positive leading coefficient, my graph will open up. It will open up. And it's called end behavior for a reason. So since our graph opens up, this is what I'm going to draw on case 1. I am not connecting the tails because this is about end behavior. It doesn't tell us what's happening between the two tails. We will figure that out later. All we want to know is, how does my polynomial open? Does it open up, down, left, right, right, left? Okay? Okay. So there's case 1. Now look at below. We have some crazy stuff over here, right? So what we're going to do here is look at the graph on the left side and look at the graph on the right side. We want to know what are the characteristics of y, like what is y doing and what is x doing on the left side of the graph and the right side of the graph. So let's look at this side of the graph. You see that your y values are headed towards infinity. So on the left side of the graph, if you look down below, we say that as y heads towards infinity, what is x doing? Well, if y is headed towards infinity, this means x has to be headed towards negative infinity. So as x gets smaller and smaller towards negative infinity, y is getting larger and larger towards positive infinity. All right, that's what's happening on the left side. On the right side, look at your y values again. Your y values are headed towards infinity again. But this time, on the right side of the graph, as y heads towards infinity, x is now headed towards positive infinity. So we are wondering, what is x doing as y is getting larger and larger and larger, right? Or you can say it the other way. What is y doing as x is getting infinitely small or as x is getting infinitely large? Okay. So there's graph case 1. Case 2, same thing, but this time our leading coefficient will be negative. So all I have to do is come back to the functions I wrote on the left side and make them all negative. That's what case 2 says. Case 2 says, hey, you have an even degree, but now your leading coefficient is negative. And if you think about transformations, what does the negative do in front of the function? It will flip it over the x-axis. Meaning that for case 2, if you have an even degree and negative leading coefficient, your graph will open down. And once again, we don't connect them because we have no idea what's going on between the ends, between the tails. We'll figure that out later in these notes. All right. Once again, left side, right side, characteristics. So look at the left side. Y values are now headed towards negative infinity. And as y heads towards negative infinity, well, x has to head towards negative infinity as well. So we can say as y gets infinitely smaller, x is getting infinitely smaller, or we say the other way, x is getting in, as x gets infinitely smaller, y gets infinitely smaller. Now look at your right side. Y again is headed towards negative infinity. But this can only happen if x is headed towards positive infinity. Okay, there you go. That's case 2. So for case 2, to keep it simple, think about football, right? Or I guess any sport, right? If you make a goal, if you score a point, if you make a basket, whatever, the referees like to go, they throw their hands in the air and they say touchdown or point good or whatever, right? They're like, yay, probably not in basketball. So like I said, just keep it with football, right? So if you have an even degree function with a positive coefficient, touchdown. If you have an even degree polynomial with a negative coefficient, you drop the ball and no touchdown. Look at that. Okay. Now, if case 1 and case 2 were for even, case 3 and case 4 are for odd. Your degree of n is odd. And case 3 is for an odd function with a positive coefficient. There we go, there we go. So now we want to think of odd functions. What is the smallest odd number? And that should be x to the first, or just x. X cubed, x to the 5th, x to the 27th, x to the 1001. As long as the degree is odd and the leading coefficient is positive, and remember I can put that as 2, 5, 9, 20, I can put that as 1000. It doesn't matter what the coefficient is, it only matters if the coefficient is positive. And if you are an odd degree function with a positive leading coefficient, then your graph will open up to the right and down to the left. And whatever happens in between is for us to figure out later. Okay, analyze it. Left side, right side. Look at the left side. Your y values, again, are headed towards negative infinity. And this can only happen if x is also headed towards negative infinity. Look at your right side. Y is headed towards infinity, positive infinity, and this can only happen if x is headed towards infinity. There it is. There's case 3. Odd degree, positive coefficient, boom, right? Like that. Or I can't see me on the screen, right? Like that. T-Rex arms. Fit in the box. Okay. And now guess what case 4 is for? In case we are odd negative. which means just say, hey, that's negative, that's negative, that's negative, that's negative, that's negative. We have an odd degree, negative leading coefficient. We can call that an odd negative. That just popped in my brain, right? Odd positive, odd negative, even positive, even negative. Ooh, might be getting somewhere with that. So this is an odd negative, odd degree, negative leading coefficient. And remember what the negative does in front as a transformation. It takes the tails and flips them over the x-axis. So now my graph will open up to the left and down to the right. Let me get rid of this. And then left side. Let's keep doing that. Stop it. Left side, right side, analyze, and look at the left side. Y is headed towards positive infinity as X is headed towards negative infinity. And right side, Y is headed towards negative infinity as X is headed towards positive infinity. And there it is. Those are the 4 cases for end behavior. If you're even, you open up or down. If you're odd, you John Travolta, or in my Zoom box, you T-Rex arms. You go this way, or you go that way. It's a new dance, okay? All right. So knowing the end behavior tells you a lot. So these cases just tell us how the graph will open, how the tails will go. All right, moving on. More definition. The real zeros of a polynomial function. So to keep this definition really, really simple, a zero of a function is the same as a root of the function, and a zero and a root all mean the same thing. You're finding an x-intercept. So if you see zeros or roots, just know that you are looking for an x-intercept. That's it. They all mean the same thing. You're looking for an x-intercept. And to find an x-intercept, you always set the function equal to 0 and solve for x. So here by the definition, if f is a polynomial function and r is a real number, then the following statements are equivalent. R is a zero of f. R is a solution or a root of the equation when you set f of x equal to 0, or when you set y equal to 0, because that's how you find an x-intercept. And if you have a 0, and if you have a solution or a root, then r is also an x-intercept of the graph of the function. This makes the point r0 on the x-axis of the graph. And if you have a 0, a root, or an x-intercept, it means you also have a factor of the function. Okay, so that's all we're saying there. That's it. A 0, a root, and an x-intercept are the same thing. They are solutions to the function, and they also make the function 0. The reason they make the function 0 is because when you plug in an x-intercept, a root, or a 0, they make the function 0, right? So let's see if I can draw an example up real fast. Let's say I had f of x equaled x minus 2, x plus 3, x minus 1. If I told you to find the zeros or the roots, it would be the same thing as finding an x-intercept. So you would set this equal to 0, and you would say, well, I can see already. The zeros are 2, -3, and 1. That's it. These are called zeros because if you plug them back into the function, you're going to get 0. It's going to 0 out. It only makes sense. It's called a root or a solution because when you plug it in, it holds true that you will get 0. And it's called an X-intercept because you can plot these as 2, 0, negative 3, 0, and 1, 0. So those are the definitions. I'll leave that there. Next definition, a polynomial function of degree n with real coefficients has at most n real zeros. So what this means is that the degree of your polynomial tells you how many zeros you have. So more examples. If my function is x squared, the degree here is 2. This means we would have 2 zeros. If my function was x to the 5th, my degree is 5. This means I would have 5 zeros. And just like the definition says, if my degree is n, then I would have n zeros, whatever n is. All right. So your degree, your exponent, your power tells you how many x-intercepts you're going to have, how many zeros you're going to have, how many roots you're going to have, right? All right. Sorry, it's hot in here. All right, the next definition. If f of x is a polynomial of degree n, then the graph of f has at most n minus 1 turning points. So before we even get into that, a turning point is where a graph changes direction. So let's say I have, x cubed. Well, what we just learned from the previous definition, if my degree is 3, I should have 3 x-intercepts. So I'll just put them here. There's 1, 2, 3. So if I graph this, I would have something like this. Well, what the next definition says, it's talking about turning points. So if your degree is n, then you have n minus 1 turning points. So the turning points for this graph would be, you take the degree of 3, subtract 1, and you would get 2. Meaning I have 2 turning points. And like I said, based off my sketch, you have 2 places where the graph changes direction. Those are called turning points. Right here would be a turning point, and right there would be a turning point. Because it's where the graph changes direction. So if you need to find turning points, you just subtract 1 from the original degree that you have. There you go. So if you just want to base it on that, we'll use the same examples that I did above. So if I have x squared, this means I have 1 turning point. If I have x to the 5th, this means I have 4 turning points. If I have x to the n, this means I have n minus 1 turning points. That's it. All right, so those are definitions. Okay, next, find a polynomial function from its zeros. Example 2, find a polynomial function of degree 3 whose zeros are negative 3, 2, and 5. So they're giving us the zeros, and we must now construct a polynomial function from the given zeros. So here's how we start. Based on the definition above, if you have zeros, right, this means there are also x-intercepts. So actually, let's look at what we did up here. So this means that they're giving us zeros, And we now must put them back into polynomial form. So all you do is you take the x-intercepts and rewrite them back as x minus or x plus the 0. That's it. We're going backwards. So these would be negative 3, 0, 2, 0, and 5, 0. Which means you would get x equals negative 3, x equals 2, x equals 5. And now to put them back into a factored form, put them back into a factor, you'll first write x equals negative 3 as x plus 3. You'll write x equals 2 as x minus 2. And you'll write x equals 5 as x minus 5. Okay. And now all it wants us to do is FOIL and distribute everything out. And you'll get your polynomial function. I want to save time, so if you want to FOIL it out, let me know during class and we can FOIL it out. But other than that, that's how we rewrite it. Okay. I assume you guys can FOIL and distribute out from here. I hope so. All right. Just to show you another format, because we'll be using it on the next page. Whenever you are constructing a polynomial back from the given zeros, we should always have a leading coefficient of a. Now, for this problem on my math lab, it doesn't ask you to put the a in there, but when we get to the next page, it's going to be important to have a, because we're going to need to solve for this actual leading coefficient. So my answer should actually be but that's when we get there. So we'll say this is proper. But this is your MML answer, of course, when you FOIL it out, though. Well, I should say distribute it, because you can only FOIL 2 of them. But okay. All right, more definitions. Now we come to something called multiplicity. So if the same factor of x minus r to the n occurs, so if the same 0 occurs multiple times, if the same x-intercept occurs multiple times, then we have something called multiplicity. So if the same factor x minus r occurs more than once, where n is any whole positive number, meaning the degree has to be a positive number, a whole number, then r is called a repeated or multiple 0 of f. Therefore, r is called a 0 of multiplicity n of f. If r is a 0 of even multiplicity, this means that the factor, the 0, the intercept, the root, shows up an even amount of times, right? It means the degree has to be even. So a good example of that would be, let's say we had x minus 1 squared. This means that x minus 1, the 0 of 1, shows up twice, meaning this would have a multiplicity of 2. If I had x minus 5 to the 10th, this means that 5 shows up, the 0, 5 shows up 10 times. I can even have x to the 6th, and this means that the 0 of 0 would show up 6 times. This is what it means to have even multiplicity. And then down below, what do you think it means to have odd multiplicity? If I did x minus 1, that would show up once, having a multiplicity of 1. X minus 5 to the 9th. This means 5 would show up 9 times. And x to the 5th. This means 0 would show up 5 times, having an odd multiplicity. So that's what it means to have even and odd multiplicity. And when we get to graphing it, if you have even multiplicity, this means that at that exact x-intercept, 0, root, the graph will touch the x-axis. Meaning, if I drew a graph here, I had the point, our graph would come down, touch the point, and go. You can even say it bounces off the point. It'll touch the point and go. If you have odd multiplicity, this means you will cross. So let's say I have a point here. If I have odd multiplicity, then my graph would come down and cross straight through it. So evens touch, odds cross. Yay. Okay. I should leave those highlighted, right? Touch, cross. Okay. Or underline, not highlighted. All right, next example just says find the zeros of the polynomial function and determine their multiplicities, and then determine whether they touch or cross the x-axis. So remember, to find a 0 is the same as finding an x-intercept. So all we have to do is set f of x equal to 0, meaning you take this whole thing and set it equal to 0. Oh yeah, 0. Okay, and now you set all of these equal to 0 and solve for x. And for the first one, you would just get x equals 0. Because if you set 5x squared equal to 0, you'd get x squared equal to 0, you'd square root, and you'd get x equals 0. Okay, but what we want to note on this is that degree of 2. This means that at x equals 0, we have a multiplicity of 2, which is even, meaning that if we were to graph this, we would touch. Okay, and then next one is x plus 2. This only has a degree of 1. So you would get x equals -2, which has a multiplicity of 1, which means it will cross. And then last one here, that has a degree of 4, which means you would get x equals 1/2, which has a multiplicity of 4, which is even. And if we were to graph it, we would touch. All right, that's all we're looking for there. Number 4, same exact process. All right. So set f of x equal to 0 and set all of this. And when I set all this equal to 0, first thing I notice is that this is not completely factored. That is a difference of squares, so I'm going to factor it. And x plus square root 3 squared. And we set it equal to 0. Okay, It is completely factored. So set each term equal to 0. So for the first one, you'll get x equals 0. And this had a degree of 1, which means you have a multiplicity of 1, and you will cross. Second one is x plus 2. You'll get x equals 2. That has a degree of 1. Multiplicity of 1, and cross. Next one has a degree of 1, and you'll get x equals 2. Again, multiplicity of 1, and cross. Last one, you'll get x equals the negative square root of 3. That has a degree of 2, which means you have a multiplicity of 2, and you will touch. That's it. Okay, so that's how multiplicities work. The next page, we're going to be given a graph. We have to examine the graph and look at the x-intercepts if the graph either crosses or touches. That will give us some information about it. So let's try it out. Okay, so this example says write a polynomial function from its graph. All right, we are given the graph, and the first question says, what is the minimum degree of a polynomial function that could have the graph? So remember, if you think about the definitions we read on the last page, however many times, what is it? I don't want to say how many, I'll say that in a second. Your degree depends on how many zeros you have. So your degree depends on how many zeros you have. Your degree depends on how many x-intercepts you have. So put that together when you look at a graph and look at your x-intercepts. You'll have an x-intercepts where you cross the x-axis or where you touch the x-axis. So put that together and we have an x-intercept here because we cross the x-axis. We have an x-intercept there because we cross the x-axis. And we have an x-intercept there because we cross the x-axis. So now, how many times do we cross the x-axis? We cross it 3 times, meaning the minimum degree can be 3. Right? The minimum degree is 3. All right. Second question. Is the leading coefficient of the polynomial positive or negative? Now, this goes back to the very first page of end behavior. How does this graph open? Look at the tails. This graph opens top left to bottom right. Top left to bottom right, right? I'm gonna squeeze in to fit in my screen. Top left to bottom right, which means we have an odd degree. And if you go top left to bottom right, reference the first page, you will see that we have an odd negative. We have an odd function with a negative leading coefficient. So we have a negative leading coefficient because of the tails. We go up to the left and down to the right. Next question says, what are the x-intercepts? Well, let me zoom in here. Hopefully we can see them. And I have x-intercepts at negative 1, 0, 1, 0, 2, 0. Those are my x-intercepts. So that's what we can write down there, right? Negative 1, 0, 1, 0, 2, 0. Now it would ask us to build the polynomial function based off the graph, based off the zeros, based off the degree, based off the coefficient, everything like that. So when we build this polynomial function, we're going to start off with f of x equals some number a. This a is going to represent the leading coefficient. And we already know that the leading coefficient is negative. So solving for a, and if a comes out negative, it's going to prove to us that we were correct. So we have to find the value of a. So what we're going to do is take these x-intercepts and rewrite them as factors, as we did on the last page. So negative 1, 0 becomes x plus 1. 1, 0 becomes x minus 1. 2, 0 becomes x minus 2. Okay. And now, what we have to do is solve for a. So in order to solve for a, we have to have been given another piece of information from the graph. So if we look back up at the graph, we see that there's a piece of information we can use here. Because in order to find a, we need to use another x and y value that's on the graph. We can't use an x-intercept because what will it do to the function? Remember that if you plug in an x-intercept, it is the same as a 0. So if you plug in an x-intercept back into the function, it's going to zero out the function and give us no information. So we see that we can work with this point, the y-intercept at 0, negative 1. So we'll say use 0, negative 1, which means, remember, points are given as x, y, which means you will plug 0 in for every x. So you'll have f of 0 equal to a times 0 plus 1, 0 minus 1, 0 minus 2, and then you'll get f of 0 is a times 1 times negative 1 times negative 2, which will give me f of 0, and then negative 1 times negative 1 times negative 2 becomes positive 2a. Okay, but then remember, we're plugging in 0, negative 1, so this means that f of 0 becomes negative 1, because when x is 0, y is negative 1. You get negative 1 equals 2a, and therefore a is equal to negative 1/2, which proves what we said in B. We said the leading coefficient will be negative. So all we have to do is take negative 1/2, plug it in here, and we're done. We have the actual function that belongs to that graph, or one of the many functions that belongs to that graph. And the reason I say many, because we went with the minimum odd degree of 1, right? Well, actually, No, this one is the graph because it said the degree would be 3. Well, that's the minimum degree. So you get 1, 2, 3, right? That is the minimum degree that this graph can have. So yeah, actually there is a lot more answers. But like I said, we're keeping it simple and going with the simple answer. So this means our final answer is -1/2 times x plus 1 times x minus 1 times x minus 2. And there it is. This function can represent that graph. Okay, well, that was fun, right? Let's do it again one more time. All right, and again, if it asks you to distribute all of that out, distribute it all out. Distribute it all out. I'm trying to save time on the video. I think it's running a little long, so let's keep going. All right, 6. Same thing here. What is the minimum degree of a polynomial function that could have the graph? And once again, we look at how many times we cross or even we touch the x-axis. So left to right, 1, we cross there. 2, we cross there. But then look at 0. Do we cross or touch? At 0, we touch. So this means that 0 is going to have an even multiplicity. And then at 2, we cross. So we know that this is odd, so this can be 1, that can be 1. That has to be 2 because it touches, and that's 1. So what is the minimum degree that this graph could have? And add those up. 1, 2, 4, 5. This can have a minimum of degree 5. All right, so you have to be careful when looking at it. You want to know, does it touch or does it cross? And if it touches, we use the smallest even degree, which is 2. And now, look at your tails. You open left, bottom left, you finish top right, which means that we have an odd positive. An odd positive. You would reference the first page again, right? So our degree is odd, and our tails open left, top right. So this means that the leading coefficient would be positive, because our tails do that. Okay. What are the x-intercepts? Well, look at the graph again. And I have, it looks like -3, so -3, 0, -1, 0, 0, 0, and 1, 0. Okay, those are my x-intercepts. Write them down here. And 1, 0. Okay. And now it says, build the polynomial function. What is our polynomial function? Okay. So that means take these x-intercepts, write them back into factored form. So you'll have f of x, and we'll start with a, because we have no idea what the leading coefficient is. So our job is to solve for a. And here we go. -3, so you'll have x plus 3. -1, x plus 1. 0, 0. We'll just say x minus 0. But remember, what did the graph do at 0, 0? The graph touched. So this means that the graph on the power on x minus 0 has to be a 2. And then x minus 1. Now we said we would have a minimum degree of 5. We'll add them up. 1, 2, 4, 5. All the degrees are there. Now let's put it together. And x minus 0 is just x squared times x minus 1. And then what I'm going to do is just move the x squared to the front. Ax squared times x plus 3 times x plus 1 times x minus 1. Everything's where it needs to be. Perfect. Okay. So now we want to solve for a. So I'll just say could have done it on the last one to be neat. And to solve for a, we need an xy value that is not an x-intercept. And lo and behold, there it is, given to us, -2, 16. That's what we'll use. And plug in -2 for every x. So running out of room there, so continue there. Actually, I can go a little higher, right? And 4 times 1 is 4, and 4 times 3 gives me 12. So this gives me 12a. Okay. And then remember that when x is -2, y will become 16. So this becomes 16 equal to 12a. Divide by 12. And we get a is 4/3. And now to finish up our final answer, we take this and we'll have 4/3 x squared times x plus 3, x plus 1, x minus 1. There we go. And that's it. That is the polynomial function. last two. Let's see. It's probably going to be a long video. Let's just knock it out. You can watch it on fast forward on YouTube. All right. How to analyze the graph of a polynomial function. Okay. Let f of x equal x minus 2 squared times x plus 2 times x plus 4. Determine the end behavior. So remember, to determine the end behavior, we need to know the degree and we need to know the sign of the leading coefficient. So here, this is in factored form, which means if it's in factored form, we must add up the degrees that are outside my parentheses. So I get 2, 1, 1. So this means that my degree is going to be 4. Which means it is even. Okay. And then my leading coefficient, which is right here, is a 1, right? Even if I said x times x times x, the leading coefficient would still be a 1. So leading coefficient is a 1, which is positive. So right now we have an even positive, right? An even positive. So this means if you look at your cases, this would be a case 1. You have an even degree, positive leading coefficient, you open up. Touchdown, right? Okay, but the way my math lab wants you to answer this is to show, it's going to say, your function resembles this power function for all absolute value, positive absolute values of x or something like that. So again, if I decided to distribute all of this, well, this would be x squared, and x squared times x would be x cubed, and x cubed times this x would be x to the 4th. So we can say that this function will resemble the power function x to the 4th. So oops. X to the 4th. Okay. Okay. So this will resemble the power function x to the 4th that will open up like this, right? So now, once again, we figure out what's going on in the middle, and what happens between the two tails is about X-intercepts and multiplicities. So this next step is find your X-intercepts and Y-intercept. Okay, so looking at the function above, if I go for my X-intercepts, we know we let f of x equals 0, meaning that this x minus 2 squared is going to give me x equals 2, and also the point 2, 0. This factor will give me x equals negative 2, and the point negative 2, 0. And this factor will give me x equals negative 4 and negative 4, 0. So those are the X-intercepts. To find the Y-intercept, you just let x equal 0. So you plug 0 into the whole function. So you'll get f of 0, and I'll have 0 minus 2 squared times 0 plus 2 times 0 plus 4, and you'll get negative 2 squared times 2 times 4, which will give me 4 times 8, which gives me 32. So our y-intercept is 0, 32. Okay, next is multiplicities of the x-intercepts of our zeros. So let's look at 2, 0. I'll just write it here. Let's look at 2, 0. 2, 0 came from x minus 2 squared. That degree was 2, meaning this will have a multiplicity of 2, which means we will touch. And then let's look at the next intercept at negative 2, 0. That one had a degree of 1, meaning it will have a multiplicity of 1, and we will cross. And then the last one was x plus 4, so that was negative 4, 0. That has a multiplicity of 1 and will cross. All right, so we've got the multiplicities down. We got whether they touch or they cross. And now, how many turning points do we have? Well, that goes along with our degree. Our degree is 4. And remember, turning points is degree minus 1. So turning points is going to be our degree of 4 minus 1, which will give me 3. 3 turning points. We are now ready to graph. All right, so let's go ahead and plot our x-intercepts, our zeros. I have one at 2, 0. So we'll put this there. I have one at 2, 0. Negative 2, 0. And negative 4, 0. I have a y-intercept at 32, so I'm going to make my y-intervals by 10. So let's say, so I'll zoom in here. This is negative 4, negative 2, 2, and then I'll say 10, 20, 30, 40. And my y-intercept is at 32, so I'll plot it right there. Okay, and now we will graph based on the end behavior and based on the multiplicities. So let's do that. So the first part of my end behavior, if you look at the top, my tail goes up and to the left. So that's how we'll start. I go up and to the left, I come down, and as I get to negative 4, will I cross or will I touch? And at negative 4, we cross. Cross, come back, get to negative 2, and then decide again, at negative 2, do I cross or do I touch? And we cross again. So we come up, we go through the y-intercept, we come back around. Oh, not that curvy. And as I get to 2, will I cross or will I touch? And at 2, we touch. We touch the point, and we go. And that's it. That's all we have to do. Our tails go with what we said in A. Our X-intercepts and our multiplicities go with what we did in C. And there's just my Y-intercept. So that's all you have to do. Graph it by the end behavior and the multiplicities of your X-intercepts. That's it. Crazy, I know, right? And again, this is just a sketch. It's not perfect. It's just a sketch. We have no idea how far this hump goes up or goes down. That's why it's a sketch. That hump could go all the way to like negative infinity, and we wouldn't know unless we actually graphed it on the calculator. But again, we're just sketching. Doesn't have to be perfect. Last one. Let's just knock it out. We're here. This might be an hour and 40-minute video, but let's get it over with. And for this one, you can just watch me work. I'll talk through it. All right, so let's get started. First is end behavior. So here, if it's not in factored form, you go with the highest power of the leading term, which is x to the fifth. So my degree is 5, which is odd. My leading coefficient is -1, which is negative. And this function will look like it says, what does it resemble? And we say resembles the power function of x to the fifth. That's all we say, resembles x to the fifth. Okay, and since we have an odd degree with a negative leading coefficient, we have an odd negative, we John Travolta, right? We John Travolta. We open top left, go bottom right. There's my end behavior. All right, on to the other stuff. X-intercept, Y-intercept. X-intercept is going to take some work because it's not factored. So we have to factor this. So for X-intercept, we know that you let f of x equals 0, and you get x to the fifth plus 5x to the fourth plus 4x cubed minus 20x squared equal to 0. You see you have an x to the fifth, an x to the fourth, an x cubed, and x squared. We can factor out an x squared. I'm going to take out a negative x squared, and I'll get x cubed minus 5x squared minus 4x plus 20. Make sure I did that. So good, negative, negative, positive. And now we have a 4-term polynomial on the inside, which means you can factor it by grouping. This negative x squared waits on the outside, and I factor by grouping. I take an x squared out, and I get x minus 5. I take a -4 out, and I get x minus 5. Close bracket equal to 0. I factor completely, well, almost completely, and I get negative x squared times x minus 5 times x squared minus 4 equal to 0. This can be factored one more time as negative x squared times x minus 5 times x plus 2, x minus 2 equal to 0. And from here, you can get our x-intercepts as 0, 5, -2, and 2. So 0, 0, 5, 0, negative 2, 0, and 2, 0. Done. Next is my Y-intercept, which is always easy. And if I plug 0 into the original function, 0, 0, 0, 0, we get 0. Oh my goodness. Too easy. There's my Y-intercept. Now on to multiplicities. I have first 0, 0. That one had a 2 on it, a degree of 2. So at 0, 0, multiplicity of 2, we touch. Everything else here had a degree of 1. So I'm just going to sum things up. 5, 0, negative 2, 0, 2, 0, all had a multiplicity of 1, which means all of these cross. Turning points, the degree was 5, and we minus 1, and we get 4. There you are. We're ready to graph. Look how fast that was. And yeah, I'm ready to plot. My X-intercepts are 0, 0, 5, 0, negative 2, 0, 2, 0. And now all we have to do is graph using end behavior and multiplicities. All right. So the first tail starts in the top left. That's what's up there. Top left comes down to negative 2. Whoop. Not so crazy. And at negative 2, we will cross. Come down, come to 0, and we touch. Come back down, curve, cross, cross, and there it is. Nothing to it. Just graph by end behavior, multiplicity, make sure it matches up to what you wrote down, and that's how you draw a W in math. All of that work. Ridiculous, I know. And once again, it's just a sketch, so we have no idea how far these humps go. My humps, my lovely lady lumps, okay? All right. And that is 5-1 and 5-2. Nothing but fun. See you at the next one.